In this video, we want to try and find the capacitance of a spherical conductor, so spherical capacitor. So we follow the same procedure as usual. We put a charge plus Q on one conductor, and we put a charge minus Q on the other. We find the potential difference between the conductors, and then from this expression, we get Q over delta V to get the capacitance. So this is the problem we have. We have a solid inner conductor, and it has a radius A, and we put a charge plus Q on this conductor. It's completely solid. Then this is empty space. This is completely empty space. Then we have a conducting shell. So the conducting shell, the conductor is just on this very thin shell, on the outer shell. And we put a charge minus Q on this outer conducting shell. Remember, on the inner part and between the two conductors, it's empty space. So let's then try to find the potential difference between the two spheres, the two conducting shells. So we want to find the potential difference between a point, say at point A, because remember the potential everywhere on this inside the solid conductor is the same value. So if you find the potential at the surface, at radius A, it's the same anywhere else on the conductor. So we want to find the potential difference between point A and point B. So we know that the region here in between the two conductors is empty space, and if we use Gauss's law, we can show that the electric field in this region is the same as the electric field due to a point charge. That means the potential is also the same as the potential due to a point charge, and the potential due to a point charge is kq over r. Now there might be some constant involved, but if we're interested in potential difference between 2 points, then we can simply use kq over A minus kq over B. So this is what the potential difference would be between the point here and a point over here. Obviously you can take kq outside as a common factor. You can take a common denominator here, AB, then you get B minus A on the numerator. So this is what the potential difference is. So how can you read from this what the capacitance of this device is? Well, we want Q divided by delta V. So then you take the AB from the denominator here and you put it in the numerator, and you take the KE B minus A in the denominator, and you get this expression. So this is what the capacitance is for conducting spheres. And the value, as we expect as usual, the value depends only on the geometry. It depends only on the inner radius and outer radius of the conductors. Now if you want to take the limit where B, the radius of this conducting shell, goes to infinity, then we can get a simple approximation, because if B goes to infinity, you can neglect A compared to B, and then you get AB over KEB. The B's will cancel and you get A over KE. KE is 1 over 4 pi epsilon naught, so you get the capacitance is 4 pi epsilon naught A. So this is the limit, the capacitance in the limit when the radius of the conducting shell goes to infinity.